Linear equations are very useful in the real-world situation of aviation. One critical example is descent slope. One example of the importance of linear functions in aviation is Flight Air Inter 149, where a misuse of linear equations caused a major crash. To calculate the correct linear equation for the correct descent slope, we first have to define the variables. X is the horizontal distance traveled since start of descent in nautical miles, y is the altitude in feet, and 5,000 is the altitude at start of descent. We first convert the descent angle into a slope. The intended descent angle is 3.3 degrees downwards, and and for and slope in math means slope equals vertical change divided by horizontal change, or rise over run. For angle alpha, slope equals tangent alpha. Since the plane is going down, the slope is negative. So the slope equals negative tangent 3.3 degrees. When calculated, that results in 0.0576. This means for every feet forward, the aircraft descends 0.0576 feet. And when you convert, but we have to convert the horizontal distance to nautical miles. Our x is in nautical miles, not feet. And 1 nautical mile equals 6,076 feet. So for 1 nautical mile forward, the aircraft drops 350 feet because 0.0576 multiplied by 6,076 equals 350. That is our slope. M equals negative 350 feet per nautical mile. The slope-intercept form of a line is y equals mx plus b. We already know that m equals negative 350. We need to now find b. To find b, we use the known point, which is 5,000. And since b is the x is a y-intercept, since b is the y-intercept when x equals 0, and that is the starting altitude, so that's 5,000. And then we write it in our final equation, y equals negative 350x plus 5,000. Now we find the equation for the actual descent. Since the pilot entered a negative 3,300 feet per minute descent slope, we use the same variables. We first start from the vertical speed, which is negative 3,300 feet per minute. We then convert time to a horizontal distance. During approach, the ground speed is 180 knots, which is equal to 180 nautical miles per hour. Convert that into nautical mile per minute, which is 180 divided by 60, which is equal to 3 nautical miles per minute. So in 1 minute, the aircraft moves 3 nautical miles. Then we have to convert speed to slope. Slope means vertical change divided by horizontal change. And in 1 minute, the vertical change is negative 3,300 feet, and the horizontal change is 3 nautical miles. So m equals negative 3,300 divided by 3, which is simplified to m equals negative 1,100 feet per nautical mile. Then we use a slope-intercept form with a slope of negative 1,100. We still need a b, which we used the exact same starting altitude which is 5,000. So the resulting equation is y equals negative 1,100x plus 5,000. This is the final graph. This graph compares the two equations and those graphed. The 3.3 degree one successfully clears the mountain and lands properly, but the negative 3,300 feet per minute crashes into a mountain. And both are graphed using the equations below. These two have major comparisons as they both have the same y-intercept, but because the slope is different, they're not parallel and they have completely different results. Here is another example of linear equations in aviation. Here is the fuel burn graph of a 777 aircraft. It has 110,000 kilograms of fuel in total, and every hour it burns 7,000 kilograms of fuel. This can be either be written in slope-intercept form as y equals negative 7,000 x plus 110,000, or by adding 7,000 x to both sides, we can write it in standard form as y plus 7,000 x equals 110,000. When y equals 0, the fuel is out, so we calculate the x-intercept, which when we calculate it by setting y to 0, it goes to approximately 15.7 by dividing both sides by 7,000. So there's 17.7 hours of total flight time around. This scenario is perfectly represented by this graph, as the x-intercept is 15.7, around 15.7, and the slope is negative 7,000, which means negative 7,000 over 1, and the y-intercept is 110,000. So the equation and graph matches, and those two represent each other. Here's an example of compound inequalities, which are also inequalities in aviation, with the example of performance limits, such as when an aircraft flies at a normal altitude, it has to be above 3,000 units and under 7,500 units. Since the altimeter measures static pressure, not altitude, suppose H is approximated by H equals 30,000 minus 1,000 P, where P is pressure in inches of mercury measured by the static system. Controlled airspace requires this much, as stated previously, and when you substitute everything in, it becomes 3,000. 3,000 is smaller or equal to 30,000, subtract 1,000 P, which is smaller than or equal to 7,500. Subtract 30,000 from all parts, which results in negative 27,000 which is larger and equal to negative 1,000 P, which is larger and equal to negative 22,500. Divide by negative 1,000, which flips the inequality signs, which results in 27 is larger or equal to P, which is larger or equal to 22.5, which when rewrote in standard order is 22.5 is smaller than P, which is smaller than 27. So the inches of mercury measured by static system must be more than 22.5 and or equal to and smaller or equal to 27. And then on the bottom is a linear graph of it. In conclusion, linear equations are a crucial part of aviation and are used in all parts, including descent slope and fuel burn calculations.